We're going to go ahead and get started. Sorry that I'm running late this morning. We're going to talk about mechanisms, which actually, I kind of like this. I think it's interesting because it sort of shows. This is where chemists are thinking about, okay, how exactly does this reaction occur? Okay, like step by step, what comes into contact with what, and how does this thing react? Okay. So that's kind of what a mechanism is. It sort of explains a little bit more about how the chemical reaction is occurring. The balanced chemical equation, that's going to tell us the reactants and the products, right? It doesn't tell us anything that happens in the middle. So it's kind of like you get the beginning of the story and the end of the story, but who knows what's going on in the middle, okay? When you're looking at a normal balanced chemical equation. The reaction mechanism kind of tells exactly how it gets from the reactants to the products. Okay, so it's showing in detail which bonds get broken, which bonds get formed when we're making a reaction. So an elementary step, you guys don't have any fill in the blank on these, do you? It's all written in for you? Okay, so we can go through this fairly quickly. An elementary step is a process that occurs in a single step. Okay, in other words, there's in every elementary step, there's usually just one thing happening, okay? It's a very simple step, and there are usually several of those or at least a couple of those in every given chemical reaction, okay? The molecularity is the number of molecules present in an elementary step, okay? If there's only one molecule, that's called unimolecular. If there's two, it's bimolecular. If it's three, it's termolecular. Okay. Now, what this is basically talking about is if you have in a unimolecular, you've got basically one thing, and typically it's going to be breaking apart or rearranging or something like that. Okay. That happens sometimes. The most common type of mechanism is a bimolecular, where you have two molecules colliding with one another and doing some sort of reaction. Okay, termolecular is very rare because what you have to have for a termolecular elementary step is you have to have actually three molecules all colliding at exactly the same time. Okay, and that just doesn't happen that often. Usually it's a two-particle collision. Okay, so here's an example of a reaction that proceeds through more than one step. Now, I guess you do have a little bit to write on some of these here. But here's an example. You've got NO2. When it combines with NO2, it can make, well, see, it's kind of weird to write that out as the start and the end of the reaction. So you kind of have to look at both of these as the reactants, okay? So you've got your NO2 and your NO2 sort of colliding here, and they make, well, here, let me back up. Okay, let me gather myself here, and I'm going to explain this basically starting with the bottom reaction, okay, and then we'll talk about how it gets there. So this is your normal balanced chemical reaction that we would normally write, okay? NO2 plus carbon monoxide gives us nitrogen monoxide plus carbon dioxide, okay? That's a typical chemical reaction. What that doesn't show, though, is that this thing actually, we think, happens in a couple of different steps. Now, all of these mechanisms we talk about, we're going to call them proposed mechanisms, because that means that chemists think that this is probably the way that this reaction occurs. Okay, it's not necessarily. Sometimes you can come up with more than one good way for a reaction to occur. So a proposed mechanism just means this is what we think is happening. Okay, this is what makes the most sense to us. So what we think is happening here is that two NO2 molecules collide first, and you end up with NO3 and NO, okay? And then the NO3 reacts with carbon monoxide to make NO2 plus CO2, okay? And so that's, if you add these reactions together, you've got two NO2s on this side. This is kind of like the Hess's Law stuff that we did. You guys remember doing that, where you're adding these up and canceling out things that are on both sides? So we've got two NO2s on the reactant side, and then we end up with one on the product side. So ultimately we end up with one NO2 on the reactant side. That's kind of our net overall. We've got a carbon monoxide on the reactant side, so that ends up on the reactant side. And then we have NO and CO2 as well. Okay, the NO3 cancels out because it's on the reactant side and the product side. Okay, the NO3 is actually called an intermediate, which we'll talk about in a second. Okay, so one of the requirements for a mechanism is the elementary steps in a mechanism have to add up to the overall balanced chemical equation. Okay, so you haven't come up with a good mechanism unless that occurs. Now you're not going to have to come up with your own mechanisms. The AP exam does not expect you to do that. They just want you to be able to look at the mechanisms that they have come up with and know some things about them. Okay, and then an intermediate, like the NO3 that we talked about here. Okay. That's something that appears in an elementary step, but it's not in the reactants of the product. So if you looked at this reaction here, I mean, there's no indication anywhere in this balanced chemical reaction that NO3 ever existed in the course of this reaction. All right. So it's called an intermediate because it's sort of it gets formed and then used up almost immediately. So it's just barely even there. Okay. So sample problem here, it's been proposed the conversion of ozone into O2 proceeds via 2 elementary steps. Okay, so this is a proposed mechanism. We think maybe this is the way that this occurs. All right. So what we want to do here is describe the molecularity of each step in the mechanism, and then write the equation for the overall reaction and identify the intermediates. Okay. All right. So first step here. Actually, I'll just number these steps. Step 1, step 2. In the first step, what is the molecularity? Okay, first step is unimolecular. There's only one thing on the reactant side, right? So this is a unimolecular. So the first step of this mechanism involves just the splitting apart of O3. Okay, now what might do that? Think about ozone. Ozone layer, why is that a good thing? Okay, ultraviolet light tends to split this apart, okay? So you got this O3, it gets hit with some electromagnetic radiation and it splits apart. Okay, that's a unimolecular first step of this reaction. Now this right here, very unstable. Okay, oxygen doesn't like to be that way. We've talked about how oxygen is diatomic, right? So this oxygen is going to find another ozone molecule, okay, and then form O2. Okay, now what is the molecularity of the second step here? Bimolecular. Okay, so there's your answer to part A. Because you have, again, you have two reactants colliding together in the second step of the mechanism. Then we want to write the equation for the overall reaction here. So, this is a really long announcement just now. Okay. So what we need to do is just basically add these together and cancel out anything that that doesn't appear in the overall chemical reaction. So we've got 2 ozone molecules on this side, okay? So I'm just going to write B down here. 2O3. These are gas molecules. Anything else on the reactant side in our final equation? Okay, we've got this oxygen here, but that cancels out because it's on the reactant side in one reaction and on the product side on the other. And then what do we end up with on the other side? O2, how many? We have 3 of those, okay? Alright, and that looks like it balances out. We've got 6 oxygens on this side, 6 oxygens on this side, okay? So there's your balanced chemical equation for the overall reaction. Now what's the intermediate here? O is the intermediate, right? That's the thing that gets formed and then immediately used up in the chemical reaction. Okay, so it doesn't even show up. Your intermediate is never going to show up in your overall chemical reaction. All right? Okay, so let's talk about rate laws for elementary steps. Some of us are having to leave right now. So the rate law for an elementary step. I said before that the stoichiometry cannot be used to determine the rate law, and then I told you I'm lying to you. Yeah. So here's where that comes in. Okay. What's that? What? Okay. All right. Anyway, so if we're talking about the rate law for an elementary step, you actually can use the stoichiometry to determine it, okay? Unimolecular processes are going to be first order, bimolecular second order, termolecular third order. And again, we typically don't get a third order elementary step. Yeah, not right now. So, how are we doing on time? I don't think we're going to get through catalysis today. We'll see. All right. So rate laws for multi-step mechanisms. The rate determining step is the slowest of the elementary steps. So here's the example that I used for this last year, and I think it works pretty well. You go through a fast food line, okay? There are 2 elementary steps that have to happen when you are getting your fast food, okay? One is you pull up to the little box and you order your food, okay? And then the second place you have to wait, usually, is the actual window where they give you the fast food, okay? So either one of those could be the rate determining step, okay? So your fast food experience is determined by how quickly you get through both of those checkpoints, all right? Now, if you've got someone who it's like their first day at the register or something like that, okay, and you're driving through this fast food place, you know, you may have this huge backup of people, you know, because the guy's like, oh, I don't know how to punch that into the cash register, you know, and so it's, you know, it's going incredibly slow, but as soon as you get through that part of the line, they have your food ready for you, and they're just handing it out, right as you come up, because they're like, yeah, sorry about the guy on the cash register, okay? He's the rate determining step in that particular example, okay? Or, let's say that they're just, you know, cranking them out at the cash register, okay, as they're taking your order, but the kitchen can't keep up, okay? They're taking a little bit longer to make your food, and so you get through the order part, but then there's a huge line waiting to actually pick up the food, because the person in front of you has an enormous van with a family of 10, and they just ordered, like, all of the biggest stuff on the menu, right? Right, yeah, the chairs on the roof. So that's the idea with the rate determining step, okay? There is one step in the mechanism that's going to take longer than the rest of the steps, okay? And it doesn't matter how fast that other step happens. If we're waiting on that other step, the rate determining step is going to be the one that determines the overall rate of the chemical reaction, okay? So that's kind of how that works. So, okay, again, this is how we'll get into the rate determining thing in just a second. I may have jumped the gun on that. But this is how your rate law would be written based on the molecularity, okay? So if you have a unimolecular process, there's only one way that can happen. You have just one thing, okay? So your rate is going to be rate constant times the concentration of A, okay? If you have a bimolecular rate determining step, that could have 2 of A, like our, I don't know if it's necessary to do this, but here's an example of that, right? You've got, in this step right here, you've got 2 of the NO2 molecules, all right? So that's a possibility. The other possibility is you have an A and a B, like this one, okay? 2 different things that are combining. So it doesn't really matter what it is. Those are both going to be bimolecular, which means that they are second order processes, okay? And then if you have a termolecular, if that ever would happen, you have 3 molecules colliding all at the same time, then that's going to be a third order. But I mean, that almost never happens, okay? All right, so if the following reaction occurs in a single elementary step, predict the rate law. Okay, so what we're saying here, now, again, this is probably not a great assumption, okay? that this occurs in one elementary step, but let's assume that it does. Okay, so this is our elementary step. So what would the rate law be for this? Okay, so there it is, right? And that actually is based on the stoichiometry, okay? Now again, don't do that when we're talking about an overall reaction, but when we're talking about the elementary steps in a mechanism, you can use the stoichiometry to figure out what the rate law is. Okay. The reason for that is, once we figure out what the rate determining step is, the slow step in the reaction, that's gonna determine the rate law. Okay, so when you're looking at an overall balanced chemical equation, which is what we've been doing this whole unit so far, you can't know what the rate determining step is. Okay, but if they give you a mechanism, they tell you what the slow step is, then we can figure it out. Okay. If the experimental studies of this reaction shows that it has the rate law, rate equals K times H2 times Br2 to the 1/2, what does that tell us about the reaction? Okay, we made a bad assumption, right? We assumed this happened in one elementary step, and it doesn't. Okay. So if you're, this is worth saying because I've seen this on an AP exam before. And we'll actually do a sample problem like this when we get to the mechanism stuff. If the rate law that you write for this thing does not match the actual rate law, then that probably means that this right here is not an elementary step. Okay, so just keep that in mind. Okay, and now is where I probably should have talked about the rate determining step with the fast food thing, but just remember that analogy. Rate determining step governs the overall rate law. Okay, so here's an example. It's found experimentally the rate law for the reaction is rate equals K times NO2. Whoops. Is that wrong on your paper too? That's supposed to be NO2 squared. 2 should be up here. Okay. What is a reaction mechanism that is consistent with this rate law? Well, that would be difficult if we hadn't already done this example, right? You guys remember this example from earlier in the notes? What's that? Well, yeah, I mean, you could figure it out, okay? But probably what we've got here is we've got a first step or second step. It doesn't really matter, I don't think, which way you write it. We would have two NO2s reacting with one another. And I think what we decided there was that that would form NO3 plus NO. Is that right? And then the NO3 would be the intermediate here that reacts with the CO and forms CO2 and NO2. Okay. So this is the first step of our mechanism. This is really the important step. Okay. But then the other step here would have to be that the NO3 then goes on to react with CO. Okay, so good question was just asked, how do we know which one is the rate determining step? Can you tell just by looking at it? And the answer is no. You have to do this experimentally, okay? So that's how you figure out which one is going to happen slower. Now, you get deep enough into this, there may be some other ways to predict, okay? But ultimately, the way you figure this out is you do the reaction and you see what happens, okay? And now, because we know what the rate law is here, yeah, I mean, it sort of makes sense on this one. Now, I don't know that would always make that perfect sense like that. I can see what you're saying there, because the NO2 and the NO2, it seems slightly less reactive. But because they are telling us the rate law, we know this is the slow step, okay? This is the kid at the cash register who doesn't know what he's doing yet. Okay, so that's going to determine how fast our chemical reaction actually occurs. Okay, by the time you get through this first step, second step is quick. It just happens really fast. Okay, so this is the one that determines how fast the reaction occurs. All right, what if the reaction in the previous example happened in one step? Would that still be consistent with the experimental rate law? Okay, so if this happened in one step, what would be our rate law for this reaction? No, it wouldn't. It'd be rate equals K times NO2. Oh, here, I might as well write this down somewhere. Rate equals K times our two reactants, or NO2, times CO, right? Well, that doesn't look like this rate law. So that tells us again, this doesn't happen in one elementary step. Okay, so the answer is no, that would not be consistent with the experimental rate law. Okay? Alright. Now, here's where it gets a little bit tricky. It's possible for an intermediate to be a reactant. Okay? And if that's the case, so we got this, whoops. So we've got 2NO plus Br2, and it's giving us 2NOBr, okay? Now that's probably not the overall, that's just the overall reaction, that's probably not a single elementary step that's happening in, so we need a mechanism for that, okay? So, here's a possible mechanism for that reaction, okay? You guys have stuff to write down on this one? Okay. Did I make you write down the entire mechanism on that? Oh, sorry. Yeah, I don't think we're going to. We'll just do, I mean, it's on the schedule that we're going to do catalysis tomorrow, which will take about 10 or 15 minutes, so that's okay. Okay, so, again, I struggled with, do we talk about equilibrium first, or do we talk about kinetics first? In the book, kinetics comes first, but it sort of assumes that you understand a little something about equilibrium here, which is tricky because we haven't talked about that yet. So basically the first step of this reaction, the proposed mechanism for this, and again, you're not going to have to come up with these mechanisms on your own, okay? It's kind of interesting to play around with it, but you're never going to be required to do that, okay? So the first step here in this proposed mechanism is that NO collides with the Br2 and forms NOBr2 as an intermediate, okay? And then you end up with this NOBr2 plus NO, and that gives you the NOBr, okay? Now, notice here, step 2 is the rate determining step, okay? So if you were to write your rate law for this, it wouldn't be this, okay? So we kind of got a disconnect there. It doesn't look like the rate law matches up with the slow elementary step, because if we were writing the rate law the way I just told you, based on the slow step, you would think that it would be, gosh, I don't have room, rate equals K times what? NOBr2 times NO. Right? Sorry, I'm writing over the top of stuff. Right, okay, so here's the thing. It's kind of awkward to have an intermediate in our rate law, okay? Because it's not even in the chemical equation. So, you know, you have this overall chemical equation. You say, well, the rate law for this equation is this. And then people look at it and say, well, where did the NOBr2 come from? You just making stuff up? Well, no, it's in the mechanism, but it's an intermediate, so it forms and it disappears, okay? So it's just, yeah, yeah, you just don't want an intermediate in the rate law for a lot of different reasons, okay? So we've got to figure out another way to write this rate law that works a little bit better. So what we're going to do here is basically just a substitution, okay? And I'm going to show you kind of how this works with the equilibrium stuff, but if you don't understand the entire derivation, the main thing you need to understand here is that we're substituting, okay? And this the key here is that this is a forward and a reverse reaction at the same time, okay? So I could actually write this thing, the NOBr2, I could sort of substitute the NO and the Br2 in for that in the mechanism, okay? So that's ultimately what we're going to do here. But here's kind of how that gets derived. Oh, well, I didn't realize I had that written on the next slide. So I didn't have to write that. So here's what we would think the rate law would be, okay? Now notice we've got a bunch of K's going on here. We've got K1, that's our reaction rate when we're going this direction. K to the -1 is our reaction rate when we're going the other direction. Now are these going to be the same? Not necessarily, okay? A reaction may react fairly quickly one way, but have a higher activation energy going back the other direction, so it actually goes slower. Does that make sense? You remember the activation energy graphs we were talking about? Okay, so this K1 and this K-1 may not be the same, okay? Probably they're not, actually. And then we've got K2. So we've got 3 different reaction rates going in these mechanisms that we've proposed here. Okay, so this would be our proposed rate law based on the slow step 2. Okay, but we just talked about intermediates are unstable. It's hard to know exactly what the concentration of an intermediate is. You know, it's not in the overall chemical reaction, so it's weird having it in the rate law. So that's not how we want to write our rate law. Okay, so we're going to express the concentration of NOBr2 in terms of NOBr and Br2. Okay, and so and again, this is the part where, yeah, I don't think this derivation is going to make a lot of sense to you without having talked about equilibrium, because in equilibrium we talk about how to write these expressions using the equilibrium constant. So I think it's going to make enough sense just thinking about a substitution here. But I mean, here is the derivation, okay? So the definition of equilibrium here is that if we multiply this constant, this rate constant times its concentration, it's equal to the other rate constant times its concentration, okay? And again, we haven't learned that yet, okay? So you just have to take my word for it at this point. So then you can actually rearrange this thing until it becomes this whole monstrosity right here, okay? But notice these 3 right here, these 3 K's, those are all just constants, right? So we can call that K, all right? And so then our rate law becomes NO2 squared Br2. So essentially what we did here, let me go back to what I have written because I think this makes a little more sense based on what we've learned so far. I just said, okay, because this thing happens in both directions, then I can write my rate law in terms of NO and Br2 instead of the NOBr2. So I'm basically taking this and substituting it in up here, okay? And so then what you end up with is rate is equal to K times NO times Br2. Just don't have enough room here. Times, and we already had NO in the mechanism, okay? So then you end up with NO in there twice, okay? And that's where that the whole NO squared comes from, okay? So then, if you look back here, okay, that's exactly the experimentally observed rate law, okay? So we're just writing the rate law in terms of things that are not intermediates, okay? That's all we're doing there, if that makes sense. So if you ever, you just have to kind of watch for that. If you ever end up with an intermediate in your slow step, then you're going to have an intermediate in your rate law, and what you need to do is substitute in the other 2 things. And usually when they give you that sort of scenario, there's going to be an equilibrium happening here, okay? So again, this is the one part that it's going to be a little bit more of a struggle to understand before we've talked about equilibrium. But the rest of kinetics, I think, actually helps with equilibrium, so that's why we're doing it that way. Okay. In general, whenever a fast step precedes a slow one, we can solve for the concentration of an intermediate by assuming equilibrium is established in the fast step, okay? Which is what I just said. Didn't we just do this? Oh. Show that the following mechanism also produces a rate law consistent with the... Okay, so here's a different mechanism, okay? So, notice, again, we call these proposed mechanisms because there's a couple different possibilities for what could actually be happening here, okay? Sorry, hang on just one second. Okay, so, again, here's another possible mechanism for this reaction, okay? So either one of these actually would work. How do we know which one it actually does? It's kind of difficult. I mean, if we could come up with something, like if we could put something in there that maybe would react with one of those intermediates but not the other, then maybe we could figure out what the actual mechanism is going to be. But it's difficult to figure out. Yeah, I guess we could maybe do something like that. The thing is, the intermediate exists for so short amount of time, it's really hard to detect its presence. Yeah. So this is why there's two proposed mechanisms for this reaction. They both work, okay? Now this is, again, step 2 is our slow step here. So we've got the same awkward thing where we've got a an intermediate in our rate law, okay? So the rate law that we would... I have more room on the next slide. Oh, I don't. Okay. So the rate law that we would normally write for this based on the rate determining step would be into O2 times BR2, or sorry, K, times the concentrations of those two things, okay? Yeah, we're going to need to substitute in because, again, we've got the intermediate thing happening. And notice, nice and convenient, we've got an equilibrium in the fast step, okay? Now, actually, it's not really a coincidence that we have an equilibrium in the fast step because if this intermediate is unstable, which intermediates usually are unstable, then it's probably going to decompose back into this just as quickly as it's being formed, okay? So that's why we have an equilibrium here. But basically what we can do is we can substitute the two NOs in for the N2O2, okay? And then we end up with a rate law. Rate equals K times NO2 squared times BR2. Hey, that looks exactly like the other rate law that we wrote, right? Okay? So that's the basic idea of how the mechanism stuff works. We'll do some more practice on that in class. And I'm going to go ahead and stop it there. I am not sure that I would recommend coming in tomorrow morning for the catalysis thing. It's going to take me probably 10 or 15 minutes. You can if you want to. So, yeah. Okay. All right. So we'll see you guys in class.